Amazing. Thank you, Atharva, for taking this class. Over to you.
Thanks. So today's class is going to be on inequalities, mostly on Jensen. So you guys remember the last class, right? It was taken by Gunjan, and she had taken, I think, AMGM and Cauchy's.
Yeah.
Okay, cool. So, I mean, even if you haven't attended the class, I hope you'll be knowing those two inequalities. I'll just share a few problems as a warm-up. So you can start with these three problems. I'll give you some time to try them.
So if at any point, if you have any ideas, feel free to speak up.
Yeah.
In the first one, doesn't Moirhead work?
No. So like it does work, but like do these
EMGM
inequalities?
can finish it, I
EMG.
think. You can take
Yeah.
2a to the power 4 plus b to the power 4 plus c to the power 4 and then cyclic
Yeah.
Yeah,
sum.
that works. Okay. Anyone knows the second one? Oh, it's a pretty
Just
Yeah, can
expand.
I
Just
say this? Like, second one, I have.
Wait.
Sure.
1 second. Before we move on to the second one, do you want to write down the solution for the first one first? Like explain the
Yeah,
first
I'll
one
just
properly.
write down the first one. So using AMGMs, we know that this is greater than. So we know this for the holds for the first one. So this implies that
you
if
can
we
just
divide,
put a bracket, the third bracket in 1/4.
yeah. So yeah, if we simplify this, we'll basically get that. But if we like simplify this and take this for all the terms, like taking 2a to the 4, 2b to the 4, and 2c to the 4, and then add all of them, we basically get the given inequality. Like if you notice, this is in the RHS is an a square term, a b term, and a c term, and the 4 will cancel out with the 4a to the 4, 4b to the 4, and 4c to the 4. So AMGM basically solve this problem. Do you guys have any questions in this?
Okay, Avni is saying AMHM works as well. Avni, do you want to unmute and elaborate on that?
How would you use AMHM?
Can you explain?
For P2. For P2.
Yeah, P2 has like multiple proofs. I think there's one proof by like every inequality. So Avni, do you want to share your proof on P2?
Consider A plus B, B plus C, and C plus A, and use AMHM. And just simplify.
Okay, yes, that works. So I'll tell the
For P2, if you don't want to do anything, I guess even expansion works.
expansion.
Like
Uh,
take the LCM expand, and you will get a true inequality in there.
isn't that a very painful thing to do?
Like yeah, it is, but in this case, I don't think so. I'm not sure.
No, let's inequalities are already hard enough. Let's go with nicer methods.
Okay.
So I think the most common proof for this is you basically substitute like you want to make the denominators a bit simpler. So you substitute them like x equals a plus b, y equals b plus c, and z equals c plus a. Okay, and now does like someone tell me what a, b, and c will come in this format? Anyone?
I'm pretty sure it's x plus y plus z by 2 minus x.
It's close to that. Actually, a would be like x plus z minus y by 2.
Oh, right, it works. Yeah.
Yeah, so this would be x plus z minus y upon y. So each individual term will look something like this. And if you notice, this just becomes a minus 1. Oh, sorry, wait, 2y. Yeah, so this just becomes minus 1 by 2. And this becomes x plus z by 2y. So you get the final inequality as x plus z upon 2y plus y plus x upon 2z plus z plus y upon 2x is greater than or equal to 3, which is something like this. And this can be easily proved using AMGM. Just like transpose the denominators to the RHS and use AMGM.
I think we also can use like rearrangement. We can let A greater than equal to B greater than equal to C, and then use the rearrangement inequality.
Yeah, that also works. So like there, like I said, there's like a proof with nearly every inequality for this inequality. Does
Also,
anyone have any?
add one on AMHM, add one to every of the term, and we can do like AMHM then.
Yeah,
I don't know why I want to go using triangles here. ABC has sides of triangles and then both because that's a semi-perimeter distance.
no, that actually does not work because it's not given that a plus b is greater than c. So
Okay.
Wait,
yeah,
also
okay.
some people had some alternative approaches for P2. If you guys
P2.
want to talk about them, feel free to unmute and share.
Yeah, yeah.
The solution using Cauchy is basically similar to AMGM.
Yeah,
You
it's
use the
kind of,
same.
yeah. Raya, you have a proof. Do you want to share that? Is that like
Yeah,
different from the one? Yeah,
yeah,
go
I
ahead.
have done using T2. So basically what I do is in every term, like in the first term, I multiply the numerator and denominator by A, and in the second term by B, and the third term by C. So I get A square by AB plus BC plus B square by AB plus sorry, yeah, AB plus A squared by AB plus AC, B squared by AB plus BC, and C squared by AC plus BC. So by T2, that is greater than equal to A plus B plus C whole square by 2 times AB plus BC plus CA. We can write that as well, like A square plus B square plus C square by 2 times AB plus BC plus CA plus 1. The first term is greater than equal to half, and the second term is 1. So if we add that, we get greater than equal to 3 by 2.
Yeah,
I
that
think.
also works. That's a nice proof. Okay. So I hope no one has any doubts on this. You can ask if you want. Okay, so let's move on to the third one. Did anyone do the third one?
Yeah, here I think T2's works. Like Raya's idea for the second one can apply to the third.
Yeah,
So
Tito's works on this. You basically, what you want to do is you add 1 to each term on the LHS. Like basically, you first notice that the sum of all the denominators on the LHS is the same as the denominator on the RHS. And we would like to make the, you also notice that the sum of the numerator plus denominator for each term is the same, which is basically 2s plus 1. So adding 1 to every term, you get something like you get this as the general term, and you use T2s on this. So the sum of the denominators comes out to 4s plus 3. And for the numerators, we basically get the following. We like get, I think, 3 times root of a, oh sorry, yeah, 2s plus 1. Yeah, we get this is greater than or equal to 18s plus 3. Like we want to prove this, and yeah, so we get the LHS is greater than or equal to this term, and we know that these two terms are equal. So we are basically done.
I mean, you could apply T2s by just like multiplying A on numerator, denominator, B on the numerator, denominator, and then using T2s. And then we know that AB plus BC plus CA is less than equal to A plus B plus C whole squared by 3.
Yes, that also works. That's, yeah. Any other approaches? Anyone used AMGM or something like that? Okay, so fine. I don't think anyone has. So let's move on to the next section. Does anyone have any doubts in this proof?
Hello, I'm trying an AMHM. Can you tell?
Sorry?
I'm trying an AMHM by adding one on all, by adding plus 3 and plus 3 on both the sides.
Yeah.
So it will be done as A plus B plus C plus 1 into 1 upon B plus C plus 1, and similarly C plus A plus 1, A plus B plus 1. Considering A plus B plus C to be x, so x plus 1 is 1 upon x minus A plus 1 plus just like that, and is equal to 3x upon x plus 3 plus 3.
I think your approach should work out. It's probably similar to
Can you
this. Sorry.
can you tell how much HM I'm not able to convert that one upon right like that.
Oh, I'm not sure if there is a proof using HM. Like, when I did this problem, I used just Status to finish it. So I can get back to you after the class on the HM. Okay, so does anyone else have any doubts?
I think we also can do like uh, uh, set s equals to 3 or something and a by s 2s minus a plus 1 and apply like Jensen on something because s is constant and we are evaluating the function of x.
Yes, that also works. But like first we're doing the first things on the basic inequalities. So like Jensen's is the topic of the class. So we'll first let me like explain the inequality, then I can explain this solution as well. Sharanya, what's your doubt?
Sorry, I got it. I was confused then.
Okay. Okay. Now I'll explain what convex and concave functions are, and I'll also explain cyclic and symmetric sums. Yeah. Okay. Yeah. So the cyclic sum of is like denoted for multiple variables. It's denoted like this. So the cyclic sum of AB is basically, if we're assuming three variables, A, B, and C, the cyclic sum would be basically taking this term and cycling through all the variables. Like here we're doing AB first. So like it's like kind of like this. The next term will start with B, so it will be BC, and the last term will start with C, so it will be C. So the cyclic sum of AB will be AB plus BC plus CA. And similarly, we'll define the symmetric sum of AB. That would be, it's like the cyclic, but instead of only starting with the A term and like going in a cycle, we're taking all different combinations of the terms. So the symmetric sum of AB would be like, we basically write this as A to the 1, B to the 1, and C to the 0. And now if you notice, there will be six possible permutations of ABC. So like one will be ABC, which gives us the term AB. The next one will be BAC, which gives us the sum BA, which is like the same as this, same as AB. Or then there will be ACB, which gives AC, and so on. We get like, this is the sum. And notice that this is equal to 2 AB plus BC plus CA. So yeah, did everyone understand cyclic and symmetric sums?
Yeah.
Yeah.
Okay. So like you can just remember this by remembering that if there are n variables, then a cyclic sum should have n terms and the symmetric sum should have n factorial terms. Okay. So now we'll move on to convex and concave functions. So a function is basically like a function on x can be defined as anything you want in terms of x. For example, f of x could be like x plus 1. It could be like 0, which is a constant function. Or it could be like e to the x or anything basically. So to define a function as convex or concave, we have to differentiate it. Like we have to double differentiate it. So you guys know a bit of basic differentiation, right? Or you can like read the PDF that I shared in case you don't. Okay. So we basically take the double differentiation of f of x, which would be denoted by f dash dash x. And we say that the function is convex if this is greater than or equal to 0. And if this is less than or equal to 0, we take it as the function as concave. For example, let's say f of x equals x squared. So can anyone tell me what would be the double differentiation of this?
2.
2.
Just
2.
yeah, it's going to be 2, right? And 2 is greater than or equal to 0. So this would be a convex function. And somebody can tell me the differentiation of 1 by x, where x is a positive integer.
ln x.
That is what we get by integration. Like, what would be the differentiation of this? Like, this is basically equal to x to the minus
Mine,
1.
like 2 by x cube or something.
Minus x to the power minus 2.
That would be the, yeah, after you
First,
take the
yeah.
differentiation, once it will give
1 by
this.
x cube.
Sorry?
1 by 2x cube.
2 by x cube, actually, I think.
Yeah, it will be 2 by x cube.
Yeah, 2 by
You
x.
differentiate this again, you will get 2 by x cube. And I mentioned that x is positive, so this would always be greater than or equal to 0, implying that this function is also a convex function. Some examples of concave functions are like if you take x, if you take a like function like x, just a second. So if you take a function as minus x squared, yeah, this would be a convex function, a concave function, as the derivative would come out to be
Minus
minus,
2.
yeah,
Yeah.
which is less than or equal to 0. So yeah, that's basically how you would define a convex or concave function. And if you want to look at this in a graphical way, assume like this is the graph of f(x). Now, in a convex function, if you take any 2 points on this graph and you draw the line between them, then for a convex function, the graph of that function will always be below the line. So as you can see, this would be a convex function. And for a concave function, it would be the reverse. Like if you take any 2 points in the graph and draw the line between them, the graph would be above it, the graph between those 2 points. So I think you guys can see that, for example, taking a quadratic equation, like a quadratic polynomial, if the x squared term is positive, it would give us this kind of graph. So that basically implies that it's always a quadratic polynomial is always convex if the coefficient of x squared is positive, and negative, if it's negative, then it would be a concave function. So yeah, this is basically just an idea to tell if the function is convex or concave. Okay, now let's move on to Jensen's inequality. So Jensen's inequality states that for any positive reals a1, a2, and so on till an, we have these two terms. So the first one is the f of a1 plus and so on plus f of an upon n. And the other term is f of a1 plus a2 plus and so on plus an over n. Now, what would be the sign between these two? So
If
for
this is convex, like LHS is greater than equal to RHS, and if convex, the opposite. Like if
if it's
concave, the
convex,
opposite one, sorry, the
yeah,
first one,
yeah.
yeah.
So if this function, if f is a convex function, then the LHS would be greater than equal to the RHS if convex. And the opposite would hold if it is concave. Okay, so now another thing about these functions is like, assume you have an inequality which only asks for like positive reals, right? Like the function is defined only on positive reals. So basically, you have that the variables in the inequality uh, have the following, like they have a condition on them. So now assume the graph of this function is something like this, like above, after zero, it's a nice convex function, but before zero, it's something weird. So if you want to use the convexity of this function, you can state that it is convex for everything after zero. This also works in a problem. Or does everyone get this part?
Yeah. I also had a question about this. Like, assume that after zero, the graph is convex, and before zero, the graph is perfectly concave. So, can I just case bash and like do both of those parts separately and combine them in the problem? Is that okay?
Yeah, you can do that as long as you like define the ranges properly and prove that it's convex or concave for each part, like perfectly concave or convex, or you can
Okay.
use.
Okay.
Okay, so everyone else also got this part, right?
It
If you have
can
any
be
doubt.
good. It can go down after some time.
Sorry?
It might go down after some time also. So
Oh, you're talking about from zero?
no, after zero.
Oh, no, like after zero, we prove that the function is convex, like I did for this function, 1 by x, right? The double derivative gives us this, but this is positive only if x is uh, like if x is positive. So that means this function is convex only for x greater than 0. Like, do you get my point? Basically, after 0, the graph will always be convex.
Okay.
Yeah, okay. So yeah, you can define a function as convex or concave for ranges, and this is quite helpful. For example, in some problems, if it's given that a1 plus a2 like and so on is equal to n, then you can just prove that this function, you know that a1 and a2 are less than equal to n, and they're also greater than equal to 0. So you get this kind of range for x. So if the graph like is convex for this certain range, if we just prove this, then we'll be done with the problem, right?
Yeah,
Okay,
but
guys.
but
Yeah, sorry.
when the equality holds, like when the equality holds for Jensen.
It will hold, the inequality will hold for this specific range. Like if the function is concave over this range, then it will hold for this range only. It will not necessarily hold for the other parts of the function.
Okay.
Guys, if you don't want to unmute, you can like put a yes in the chat if stuff is
By
clear.
the way, when will equality hold?
That depends on like it usually holds when all of them are equal.
Doesn't that depend on the function that we're choosing?
Yeah, it also depends on the function, but like equality cases usually like when they're equal.
Okay.
Okay. So I hope all of you have understood Jensen's inequality. Let's do a few problems on Jensen's.
Can you give an example of tan x graph? Tan x.
Yeah, a tan x graph is, yes, it's an interesting graph. Tan x is basically like this, right? So does anyone want to make observations about this? This is, I think, pi by 2. Yeah, does anyone want to say anything about this?
Yeah, the graph is convex in the interval 0 to pi by 2 and concave in the interval minus pi by 2 to 0. And like, since the graph is periodic, this thing holds for other values as
Yeah, basically from n pi to n pi by 2, sorry, n plus pi by 2. This graph will be a convex graph, as like you can see, taking any 2 points, the graph will always be under. And in the, like, I forgot the differentiation of this, but I think it's sec squared x. And basically, the differentiation also, if you take it, then substituting x as a one of in this range, you'll get that it's positive. And if you substitute x from the range n plus pi by 2 to n plus 1 pi, you'll get that the differentiation is negative. So yeah, the graph will be concave for some interval and convex for some other interval. So no, calculating the double differentiation might not always be feasible.
How
Like
can I show the convexity or concavity at that time then?
in the problems that come in Olympiads, it's usually like either it's a differentiable function. Like functions are usually always differentiable. The Getting to know whether the differentiation would be negative or positive is kind of hard to tell. But in the problems that you get, you'll mostly have it direct, or there will be a range for which you can substitute x, or you can prove for intervals in that range whether it's positive or negative. So you can like, it's not necessary that the function will be an easy one. For example, if this one comes in the problem, you'll have to specify this range. Yeah. So like if you have the function as tan x, so the,
First derivative would be sec squared x.
yeah. So like the double differentiation of this function would come as positive in this interval only. N to n plus n pi to n pi plus pi by 2. And in the other range, that is like n pi plus pi by 2 to n plus 1 pi, the differentiation will come negative. So if you want to use this in your problem, you would have to specify that it's convex in this range and use Jensen's for that range. And if like you have to prove it if you want to prove it for a larger range, you will have to split it into cases. Okay, so is everyone clear now? You guys can put yes in the chat if you don't want to.
Yeah.
Yes.
Okay, nice. So yeah, let's move on to some problems with Jensen's. Give me a minute. Yeah, okay. So we'll start with an easy one. You need to prove the following inequalities slash. Yeah, you need to prove this inequality. For I from 1 to n, you need to prove that this holds. So looking at this problem, does anyone have an idea of what the function would be?
Root x
Root of x
plus 1.
square plus 1.
Sorry?
Just root over x square plus 1 equals to f.
Yeah, So yeah, that would be the function that we're considering here. So can somebody tell me what we get as the double derivative of that function? Anyone? You guys can message in the chat as well.
Minus 1 by 4 I square plus 1 to the power minus 3 by 2. I'm not sure if this is correct, but
Sorry, can you type it?
okay.
Wait, like taking square roots keeps the convexity of the function same, right? So we can just like take the second derivative of x square and that will also x square plus because like taking roots does not change the convexity.
I see. That's new to me as well. Okay, that's cool. So I'll just believe you. So yeah. Anyway, the function gives us we get that the function is convex anyway. So we basically want to use Jensen's on this now. So the sum of all the functions upon n would be greater than equal to the sum of the averages, the function of the averages. So yeah, we get this is the LHS and the RHS would be
Like, how did you get the function is convex?
you take the double derivative of it. And in this case, the double derivative comes out to be positive. So we get that the function is a convex function.
Okay.
Can you write on whiteboard?
Sorry?
Can you write on whiteboard?
Okay, I'll do it.
What do you want to write? Should that?
I was saying to write on whiteboard. Possible.
Okay. Oh, you want me to write on a whiteboard? I'll do it in one. Yeah, okay. So on the LHS, we would get that sum of I squared plus 1. Uh, this upon n is greater than equal to, now the average of all of these would be basically n plus 1 by 2. The average of 1 to n is basically this. And this is f of n plus 1 by 2. So now, as we had seen earlier, the function we had defined is f is equal to f of x is equal to root x squared plus 1. So we get this is equal to root of x squared plus 2n plus 1 by 4 plus 1. Right. And this is basically equal to Okay. And now if you go back to the problem, you'll see that the what we required to prove was this. Yeah, we wanted to prove this, and sorry, wait. I think
I
it
think
got copied.
there's a square root
Yeah,
missing
there's
there.
a square
Yeah,
root over it.
yeah.
It got copied wrong, I think. But yeah, you can see that the n transposes to the other side, and you're basically done.
Yeah.
Okay.
Sorry, I think Manda mentioned that if f of x is convex, then root of f of x is also convex. Why is that true in general?
Actually, I'm not sure about that. I also didn't know about this.
Okay.
I'll check it out after the class and get back to you guys on.
Yes. Thank you.
Okay, so yeah, there was this problem I had given you in the beginning. Let me just paste it here. Yeah. So for this problem, some of you mentioned that there's a solution by Jensen. So I was actually going to take this problem again. But yeah, you guys can tell me the solution of this using Jensen's. Anyone?
Can we take the function a by 2s minus a plus 1? Just a guess.
Yeah, that is basically the idea.
Yeah.
You take f of x equals x upon 2s minus x plus 1. And you double differentiate this, and it comes out to be a convex function. Okay, so in this problem, you need to note that since we are talking about a plus b plus c, we can assume a plus b plus c to be a constant and just assume that a, b, and c are variables that add up to 2s. So we're taking 2s as a constant and a plus b plus c as a, b, and c as variables from in the range 0 to 2s. So basically, we'll get that the denominator is always positive, and obviously, so is the
I have a
numerator.
question. In a contest, can we like directly write down that it is convex or concave, or we have to show the differentiation by doing it in the paper?
Yeah, you will have to show it by doing the differentiation.
Okay.
No, I mean, can you even use Jensen without?
Well, no, you have. If you want to use Jensen's in contest, then you will need to prove that the function is convex. But that doesn't take like more than 5 minutes. So you just need to differentiate.
No, the function is convex, that is understandable. But do we need to prove what is the Jensen inequality?
No, you can state it. It's you can use this in RM. Just stating the inequality and proving that the function is convex is enough. So yeah, you basically get that this function is a convex function. And if you find the average of this, it will come out to be like 2s upon, yeah, 2s upon 1. Substitute, yeah, 2s upon 1 by 3. Yeah, okay, sorry, my bad. So like the average of a, b, and c would be 2s by 3. And if you substitute that in the function, you would get something like this. And in the LHS, you would get a upon 2s minus a plus 1 or b upon 2s minus a plus 1. This is that the LHS is basically greater than equal to this. And if you notice that multiplying 3 on in the numerator and denominator would basically give you the RHS. So yeah, you get this is greater than equal to. And we're basically done with the problem. So Jensen's gave us an instant solution to this problem.
If you multiply it by 3 on both sides, then won't you get like 2s, not 6s?
Yeah.
But
No,
you
but
need.
like there's this whole thing upon 3, right?
Acha, right.
Yeah,
You
so
have
that basically gives
3.
6.
I'm
Yeah.
sorry, but like, can you show the double differentiation to this?
I like, okay, it's like it will take a bit of time, so I'll just tell you after the class because like it's a fraction, so it takes time. Okay, so yeah, you need to like by using Jensen's, you need to be careful to remember that it's the average. If we're taking the average of the functions here, you can't disregard this n. Okay. Hang on a second. I'll just copy paste another problem. Oh, okay. There is one more interesting thing. Does anyone know about the proof of AMGM using Jensen?
I had seen it, but now I
Yeah, I also think that.
have.
You just prove the.
Okay, wait, guys. If somebody hasn't seen it, we'll let them try. So like, I'll give you guys 5 minutes. This is an interesting problem. Uh, I'll give you a hint. You use one of the functions that is given in the PDF, but like, yeah, you guys can try this for a while. AMGM is basically proof that sigma AI. Yeah, you guys can try this for a while. Also, if you want to give any ideas, then like send a private message. So yeah, people who have not done this before, any ideas? You can send to everyone. Yes, logarithm is the correct idea. So you basically take like the function as f of x equals ln of x, and to check the this function, we take the double derivative, taking one derivative, we get 1 by
1
x.
by x and the second one minus 1 by x squared.
Yeah. So this is basically a concave function, since like in AMGM it's like given that they're all positive reals. So yeah, this function will always be concave. Okay, so now we'll take ln of a1 plus ln of a2 and so on, since we're applying Jensen. So this would be the LHS term, right? And the RHS term would be ln of a1 plus yeah. And now since we have that the function is a concave function, the sign of the inequality is reversed. So basically, this is greater than this. And now using the properties of log, I'm sure you guys will be knowing. So we get ln of a1, a2, and so on, an to the 1 by n is less than equal to ln of the RHS.
Yeah, now you just cancel it.
Yeah, we can cancel the ln since like we know that e is greater than 1. So that does not cause any negativities. And we basically are done with the proof of AMG.
Wait, like in log, we are only on positive basis, right? Why do we need to care about that?
No, the problem would be that if you like take a base, say 0.5, then canceling the ln on both sides would reverse the inequality sign. Because log of like a base which is less than 1 would be negative. Like ln of, oh sorry, log to the base 0.5 of 2 is minus 1, right? So
Right.
we need to be careful about this as well. So yeah, here the motivation for taking logarithm was you see power. So basically we want to like kind of cancel out that power. And we know that ln of x has a very nice derivative. So yeah, if we basically use that property of ln. Okay, I'll share another problem for Jensen's. So some of you might have seen this problem. Oh, it's like kind of well known. You are given that A, B, and C are positive reals such that A plus B plus C is equal to 1 by A plus 1 by B plus 1 by C. And you have to prove the following inequality. Yeah. So I'll give you some time to work on this. This is a slightly harder problem. So if anyone has ideas, like message me privately. Okay, so like many guys have messaged me saying that we'll take A plus B plus C as a constant. So yeah, you can, that is a correct, that is a good idea. You can take this as S, let's say. So yeah, this is the first thing. Okay, so any ideas for what f might be?
1 by s, fx is 1 by x plus a whole squared or something like that.
Yeah. You basically notice that in all of the denominators, it's like a plus b plus c and plus a, b, or c. So this gives us motivation to think of the function as f of x equals 1 by s plus x squared. Okay, now what do we do next? What is the continuation for the, what do we do on the RHS? That is the important part.
We can show that the function is concave and apply the Jensen.
Yeah, that's correct. This function is a concave function. So yeah, we'll apply Jensen's on A, B, and C individually, and we get that the LHS sigma 1 by this is less than equal to the average of these would be A plus B plus C by 3.
S
So
by
that,
3.
yeah.
I'm sorry, how's it 4s?
Oh, because the function is S plus X.
Oh, okay.
Now we can just open up the things and see
Yeah,
that
but
we will get
that would just,
RHS is coming out to be 27 by 16 s squared. So I don't think.
RHS is coming out to be 27 by 16
16
into
s
1 by
squared.
a plus b plus c whole square.
yeah,
Yeah.
that is basically this. Right.
Now we can like break x square to be a plus b plus c into 1 by a plus 1 by b plus 1 by c and show that it is greater than equal to 9 and so it would be less than equal to 9 and it would come out to be 3 by 16.
Yes, that's the correct idea. So you like write this out as there's actually one more interesting idea on this. Do you guys want to say anything on this? It gives a direct solution. Like you don't need to expand and prove that this is less than equal to 9.
No, I didn't expand. I said that like
2s.
we can break a plus b plus c whole square into a plus b plus c
Yeah,
and
yeah,
1 by a plus 1 by b plus 1 by c.
yeah. That is less than equal to 9. But like there is a more kind of direct
We
method.
can also
So like a plus 1 by a is
we can
at
also
least
say
2
that
almost.
2s equals to a plus b plus c plus 1 by a plus 1 by b plus 1 by c, which is greater than or equal to 6, and so on.
Sorry. Oh, can you repeat? Your voice is very low. Or you can like type in the chat.
I think, yeah, 2s is equal to a plus 1 by a plus b plus 1 by b plus c plus 1 by c, that is greater than equal to 6. So s is greater than equal to 3. So the whole thing is less than equal to 27 by 16 times 9.
That's correct. Uh, okay, there's another method. You guys know, do you guys know about homogenization?
A little bit.
You
Yeah.
just have to like given the condition, you need to apply it in such a way that the degrees of both the sides become same.
Yeah. So, yeah, you have basically if you substituted, you multiply this by 1, and you get that in the numerator you can substitute 1 by a plus 1 by b plus 1 by c, and in the denominator you can substitute a plus b plus c. So now you get that the LHS has a degree of -2, you can say, and the RHS also has the similar degree because you substitute 1 by a upon a, the sum of this. So yeah, this equal you can make this inequality homogeneous, and if you have this, then you can take a plus b plus c to be any constant you want. Like you can assume it to be like 1 or 2, and that will still give you a correct answer. So yeah, that is kind of an advanced method. You guys don't need to like know this right now, but it's just a nice method. So in this case, for our convenience, we'll substitute s equals 3, and that just cancels out. But yeah, this method is a better one. So you have a plus 1 by a, or sigma a plus 1 by a is greater than equal to 6, and this is equal to 2s. So you basically get s is greater than equal to 3, which implies that the LHS is less than 27 upon 16 into
9.
9,
3 square.
which is equal to 3 by 16, which is what we wanted to prove. Okay, so how did you guys find this problem? Like, was this a bit easy or like doable for you guys?
It was
Kind of easy.
It was easy, right? Okay, now you guys
without the
would know this,
differentiation
guys,
part, the rest of the thing was easy.
other than the differentiation
Yeah,
part.
true.
I mean, differentiation is basically just apply the formula. There's nothing much to do. It should not take more than like 10 minutes to differentiate any function. Like just remember
It's
all the
only time
formulae.
consuming. It's not difficult, but time consuming.
Yeah. So yeah, you guys will probably be surprised to know that this problem is actually an IMO shortlist problem. This is ISL 2009 A2. So
I think I've seen this problem before. Like, is this a very common one?
yeah, it's kind of common. So like you can see how Jensen's kind of trivializes even hard problems, and like it's even quite intuitive to use Jensen's because you notice that all of the terms have something in common, and the RHS has only one term. If you have this kind of condition, then you should think of applying Jensen's. Okay.
Is there any alternate good solution without Jensen?
Oh yeah, there are solutions by AMGM, but those are like longer, like very long. Uh,
Oh,
I don't like have the solutions with me right now. Like I don't remember the solutions with AMGM, but yeah, they exist. I think if you go on AOPS, you can find. So is everyone clear about Jensen's? Like, has everyone completely understood Jensen?
Yeah.
Guys, everyone say yes.
yeah.
Does anyone have any doubts in Jensen? What's your doubt? Oh, okay. So, okay, no one is asking any doubts, so I'll just assume it's clear to everyone. Uh, we have, I think, 20 minutes left, so I'll move on to Muirhead's inequality. So for this, you will require a definition that is majorization. So majorization is defined over sequences. If you have two sequences, sequences are denoted like this, A and B, such that both of these sequences have n terms. You have A1 and so on till AN, and you have B1 and so on till Bn.
Finite sequences.
Yeah, finite. Okay. Now, a majorization has a few conditions. So the first condition is that the sequences are increasing. I'm at decreasing. A1 is greater than equal to A2 and so on till AN. And the same holds for the B sequence. The second condition is that the sum of AI is equal to the sum of BI. And the third condition, and this is the most important one, for any 1 to j, A of I is greater than or equal to P of. So what this third condition basically means that, so basically the second condition implies that A1 plus and so on till AN is equal to B1 plus and so on till Bn. The second condition states that for all j from 1 to n minus 1, the sum of the first A terms, like first AI terms, is greater than or equal to the sum of the first BI terms. So like you basically have, if you have a four terms in each sequence, so you will basically have A1 is greater than equal to B1, then A1 plus A2 is greater than equal to B1 plus B2, and A1 plus A2 plus A3 is greater than B1 plus B2 plus B3, like, greater than or equal to. This is what the third condition means. For yeah, so do you guys get the majorization?
Yeah.
Oh guys, everyone please respond.
You can
Yes.
give a thumbs up or just put it in the chat.
Yes.
Yeah, you can like respond in chat as well, that works. Okay, so nice. So like I'll just give a small example. If you have a sequence like 7, 3, 1, and you have a sequence 5, 4, 2, then like what would be which sequence would majorize which one?
731 will majorize
First
5.
one measurizes second.
Yeah, majorization is denoted by this symbol. It's kind of a curved greater than sign.
Greater than, yeah.
Yeah, so these are in decreasing order, which is the first condition. The sum of both sequences are the same, and 7 is greater than 5, 10 is greater than 9, and yeah, that's basically all the condition. So yeah, now we have defined majorization. So let's move on to Muirhead's inequality.
If like
This
a summation of I equals to 1 to n ai is also greater than summation of I equals to 1 to n bi, then the majorization would not work.
sorry, if
Like for the j when is j when it is equal to n and the sum is also not equal greater than, then the majorization would not work.
So you're saying like if j is equal to n, that is basically the second condition, right? This is from
Yeah,
1 to
but if it is not equal and greater than,
yeah, then the majorization does not work. All of these three conditions have to hold for majorization to work.
okay.
The sum of all terms has to be equal. Anything below that, one has to be greater than the other, like the same one each time. Okay, so like you guys know about bash in geometry. So this inequality is basically kind of a bash in inequalities. It kind of makes 20% of all inequality problems like trivial. So you have that for two sequences, A and B with n terms. And you have
Like
variables.
whether it works for only symmetric cells, so does it really make 80% trivial? Because many of them are not symmetric. So
It actually does. I'll just give some examples to show you. You have x1,
Can
x2,
we
x.
permutate in?
Sorry,
Can we permutate the A1, A2, A1, and B1, B2?
you cannot permutate them directly. Like in a sequence, they have to be in decreasing order, like in the initial sequence. Is that what you wanted to ask?
Okay.
Okay, so you have all of these are uh, positive reals, and an and bn are two sequences, such that an majorizes bn. Then Muirhead's inequality states that the symmetric sum of x1 to the a1 blah 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 xn to the an is greater than equal to the symmetric sum of x1 to the b1 and so on. Does
Are
everyone?
x1 to an real numbers?
Yeah, they're all positive reals.
Positive reals.
Otherwise, like you would get very weird stuff with the sign and stuff.
Yeah.
So does everyone get this? This is the statement of Muirhead's.
Yeah.
Yes.
Okay, nice. So I'll give some problems for you to try. First is an easy one. Yeah. So what are you going to do on this problem?
Can I like say it or should I like message?
Oh yeah, you can message me. I'll anyway share the solution in 2 minutes. So Okay, so I'll give the solution of this one. You have on the RHS, notice that on the LHS, notice that the degree is 2, and on the RHS, the degree is 1. Right. Now, if you want to apply Muirhead's, notice that in Muirhead's, the degree on both sides is the same. So you want some way of making the degree of the RHS equal to that of the LHS. And
We
that's
can
where we
multiply
have,
cube root of ABC.
sorry.
We can multiply cube root of ABC to the RHS.
Yeah, that's basically what we're going to do. So if you multiply the cube root of ABC, notice that the cube root of ABC has degree 1. So that would make the RHS like a to the 4 by 3 plus, no, sorry, a time, plus, wait,
Yeah, P to the 1 by 3 and C to the 1 by 3.
yeah, it would be the cyclic sum of this. Yeah. Okay. Now for Muirheads, we need like a symmetric sum. So first, consider the sequences 2, 0, 0, and
Can we interchange the terms in it? Like shift A to A square side, LHS side, and C to LHS side?
like this.
Yes, like 2, 1, 1, and 1, 2, 2.
How does that help us?
Sorry.
Like we don't know that a is greater than 1, right? So we can't say that a square is greater than 3. Yeah, so in these two sequences, the sum is equal on both sides. They are decreasing, and 2 is greater than 4 by 3, 2 plus 0 is greater than 5 by 3, and
First one majorizes the second one.
yeah. So by Muirhead's inequality, you get that the symmetric sum of LHS is basically A2, B0, C0, which is equal to 2 times A square. Like because you can get A square B0 C0 and A square C0 B0. So like basically it's going to come out as 2 times A square plus B square plus C square. And similarly for the RHS, you will get that RHS is equal to symmetric sum of A to the 4 by 3, or B to the 1 by 3, and C to the 1 by 3. And this would be like equal to a similar thing, 2 times. Yeah. So basically you get that uh, this sequence 200 majorizes 4 by 3, 1 by 3, 1 by 3. So you get this symmetric sum is greater than or equal to this symmetric sum, which is basically what you wanted to prove, right? You divide ABC on the RHS and you get A squared plus B squared plus C squared is greater than or equal to A plus B plus C. So
How
is
do we
everyone
prove Muirheads though?
the proof of Muirheads, I'm not like sure how to prove Muirheads as well. Like the proof is like in higher mathematics. It involves matrices and a lot of different concepts. Okay. So does everyone get this solution? Oh, okay, nice. So I'll share another problem. Yeah, I'll give you 5 minutes to open this. You guys are fine with staying till like 8:40, right?
Yeah.
Yeah.
Okay, nice. I mean, if you want to leave, you can leave because I'm just going to be like doing this last problem. The theory part is like over. So does anyone have any ideas?
First, we can multiply by ABC both the sides.
Sorry, ABC? Or do you
Yes.
mean like A plus B plus C?
First ABC, then we can multiply A plus B plus C to the LHS.
Oh, okay. Yeah. So you're saying you're multiplying ABC on both sides. That will give us AB plus BC plus CA is less than equal to 3ABC.
Also, one more thing is like, one by A as A plus B plus C by A. Does that work? Like, it's like cyclic sum of 1 by A. So you get it A plus cyclic sum of A plus B plus C by A as 1 is equal to A plus B plus C. So you just separate it and then do it. Does that work?
I'll just get back to that after this
I
method.
think the idea is after multiplying ABC in both sides, the degree of the left hand side is 2 and the right hand side is 3. So we'll just multiply A plus B plus C on the left hand side to equalize the degree.
Yeah,
Yeah.
that is the solution.
Yeah.
So you get like A squared. Oh, wait. So basically, if you notice, like, there's going to be like two kind of sequences here. Like one is going to be this 1 comma 1 comma 1, and one would be this 3 comma 0 comma 0. So like basically ones will cancel out. This is the LHS. right? So this would expand to 3abc plus,
Symmetric sum of A square B.
yeah, I'll just write that. Yeah, and we know that this is basically the sequence, like we can write it like this. So we have the sequence 2, 1, 0 on the LHS and the sequence 3, 0, 0 on the RHS. So you can see that the RHS kind of majorizes the LHS, and yeah, this is less than equal, that means that this is less than equal to 3abc plus 2 sum of a cube. Yeah, so that completes the proof for this problem. Oh yeah, somebody else had some other idea of multiplying. Yeah, okay, the cyclic sum, right? You were saying, I think, b plus c by a. This is less than equal to, this was your idea, right? Whoever, someone was saying this.
Um, I guess so. Like you write 1 by A is A plus B plus C by A.
Yeah. That's what I did, right? I substituted a plus b plus c here, and like you get it like 1 plus b plus c by a. But then the 3's just cancel out. So that's your idea, right?
Hmm.
You get this as each term.
Yeah.
Hang on, how does the 3 cancel?
No, the 3 doesn't.
You have 1 plus b plus c plus b plus c by a. So like this 1 is there for all 3 of the terms, and there is a 3 on the.
Achha, that's a 3,
Right.
right? Right, that's a 3. Okay.
Yeah.
Yeah, so it cancels out. So you have B plus C by A and so on. And then you will get.
Yeah, you can like, what is the continuation of this? Oops,
Maybe after this, take the LCM, or I don't know. Like you have A cube plus B cube plus C cube by A.
It would be similar. Just multiply ABC on both sides, and you get again a kind of symmetric sum. You
It's
basically
still
get
not.
this same thing again. Okay, yeah. So, are you guys comfortable with mureheads? Like, at least, do you feel like you've understood the inequality?
Yes.
Yeah.
Okay, so for mureheads, what you need to do is you just need to make the degrees on both sides equal, and you like kind of need to ensure that every term is occurring in the symmetric sum, because symmetric sums are like kind of bigger than cyclic sums, right? They have more distinct terms. So you need to ensure like for 4 variables or for 3 different powers, all of those terms are occurring. So you
Yeah.
need to be careful of that. And one more trap that people fall into is like they assume that if the cyclic sum inequality holds, like if, for example, AB plus BC plus CA is less than equal to, okay, that's not like a good example, but like the idea is basically like if a cyclic permutation holds, that does not imply that the symmetric thing also holds. Or do you get my point? Like symmetric
The
has more
cyclic
terms, so
thing is like
Yeah.
most of the time into the cyclic thing. Can you give an example where it is not?
wait, I don't have an example right now. I just wanted to like
Like
I just remember.
a symmetric sum has like n factorial minus n more terms than a cyclic sum.
Yeah,
Say.
it has those many more terms, and if one cyclic sum holds, it's not necessarily another cyclic sum holds. Like if you have kind
Yeah.
of an a square b cube c thing kind of thing, so the cyclic sum of this would only be like a square b cube c, then b square c cube a, but like that would not include a term like a square c cube b, right? And in the question statement, if it is given like c is greater than b is greater than a, so a cyclic sum would use this condition, but in a symmetric sum you would have this extra term which is like greater in value. So it doesn't necessarily hold. Like it could hold in some cases, but it doesn't necessarily hold. You like need to be careful for. Okay, and also I have to mention the equality case for murets. Basically, equality case is like all xi are equal, or the other equality case is that the sequence an is equal to the sequence bn. Like those are kind of like obvious if you look at the inequality. Those are the only two cases that work.
Yeah.
So yeah, we're done with the class. Well, this was all I wanted to share. So are you guys comfortable with everything I took today?
Yeah.
Okay, nice.
Also, like, how will you know that where to apply the homogenization?
You will like if you see a lot of terms, like if you see every kind of term occurring, then that would probably be a good intuition to apply murets. Like if you see a symmetric sum coming up somewhere. For example, if you have like AB, BC, CD, DA, that's not an indication of murets. This is like a cyclic sum, so you would not want to apply murets here. If you have the additional terms AC and BD, that would be a kind of a motivation to apply murets.
Not only for murets, like if any inequality, if you have to solve, I guess homogenization maximum time works, but how will you apply homogenization? Like in this term, I have to apply homogenization. How will I know?
You basically find out if you're thinking of some specific inequality, you think of the degree conditions. Like in Muirhead's, the degrees on both sides have to be equal. So you need to use that as the condition.
Degree, right?
Yeah, you check the degree and basically whatever works.
And like negative degree also works, right? Negative degree. Both sides have negative degree and stuff.
I would advise you to go against negative degrees because like that does not really work well for inequalities like Muirhead's.
No, like you only did one negative degree in the class.
So sorry, where?
That was Jensen.
Oh,
Like
that was
one
Jensen.
by, yeah.
Okay, okay, yeah.
No,
Right.
for a function, yeah. If you want to differentiate a function, then that can have a negative degree.
Yeah.
That works for Jensen's, yeah.
Mhm.
But like in Jensen, it's not exactly your. It's more like your
Degree
different.
doesn't really matter in Jensen as far as I'm concerned.
No, degree does not matter. It's basically
Yeah.
about the function itself.
Yeah. Like each term has to be dependent on only one like variable, otherwise there exists no such function.
Yeah.
Okay.
You can like also try proving AMGM using Murex. Murex is basically like a generalization of AMGM. And this inequality is pretty useful. Like if you notice in Olympiad problems, you get quite a lot of terms like this, AQ plus BQ plus CQ. So like that's basically always a symmetric sum because you can like add terms like B to the 0, C to the 0 and so on without changing anything. So yeah, this inequality is very useful, but you can't use it in RM. Like they won't check your solution. You can use it in INM only.
Muirhead was, I guess, it was written in Muirhead is always provable by repeated AMG.
Yeah, I think that might be true. I have not seen that proof, but like it seems likely since it's just a generalization.
Yeah, also it told Muirhead will not work in RM.
Yeah, it will not work in RM.
That's bad.
Yeah, Muirhead's is like it kind of trivializes many problems.
Yeah.
But yeah, do not use this in RM. Do not even like quote it. Just use AMGMs and Cauchys in RM and Jensen's as well. If you want to, like, RMO has only these three inequalities mostly.
No, RMO does not have Jensen. RMO has Jensen.
RMO allows Jensen's, yeah.
No. I am asking, was there any problem in RMO that used Jensen? I don't think so.
I mean, there is always a solution using AMGM. So like that, the
Yeah, but
intended
like,
would be
yeah,
AMGM.
alternative solutions exist using Jensen of many PYQ.
Yeah, alternative solutions obviously exist. But like again, you need to be careful using Jensen's because
Like
RMO
if
grading
we
is done,
rearrange the quantity in RMO, we have to prove it.
you don't need to prove Jensen's.
No, rearrangement inequality or T2 inequality, we have to prove it there.
No, you don't need to prove rearrangement either. Like rearrangement is kind of a well-known inequality.
Okay.
It's
I don't know why, but everyone says to prove T2, whereas T2 is like the most famous inequality after M.
yeah, you can use T2s in RMO. Like it's just a like a specific case of Cauchy sorts.
Yeah, like we
Yeah.
have to prove T2, right?
No, you don't need to prove T2. You can
You don't
just
need
quote.
to? Okay, damn, that's news to me. I thought you needed to prove T2.
I mean,
Also, if
you should,
you're unsure about it, you can just quote it as Cauchy.
yeah, like just I mean,
Right.
what is even the proof of T2? Just write that it's like Cauchy but with xi upon root y. That should like just, if you're scared, then you can write that because RMO grading is done by school teachers, like so they might not know.
RMO grading is
I
bad.
think calculus is not used like allowed in RMO, right? While doing Jensen.
And no, you can use it for Jensen's. You can't use
Actually,
it as
I know
but
many people who got like 0 for using Jensen and calculus.
again, that depends on your region and your graders. So like
Yeah, West Bengal.
careful. So like
Yeah.
West Bengal's grading is also not very good, although it's
Yeah,
in ISI.
absolutely.
Also, although it's in ISI, I think student grading.
One second. Let me
yeah, this is